always have equilibrium arrows. And writing them in this uneven way emphasizes the fact that dissociation is partial. Now, there are thousands upon thousands of weak acids. There are many different kinds of organic acids that behave this way: citric acid, lactic acid, malic acid, ascorbic acid, you name it. You've probably heard of many of these acids in your biology classes. So that's the generic case. I'm going to show you a specific case using, as an example, acetic acid. So acetic acid, of course, is the acid in vinegar. Vinegar is about 5% acetic acid. And if we put acetic acid in water, it partially dissociates to give its conjugate base, the acetate ion and hydronium. So here's a hydronium ion here. So this reaction happens when we put acetic acid in water. Now, most of the molecules remain intact. So I'm going to say they remain intact, quotation marks. What I mean by intact is that it keeps the proton on. So you really have very few of the molecules actually dissociating into ions. So here we have the conjugate base of acetic acid, and here's where I would ask you what the name of it is, but since I'm just talking, I'm going to tell you that it's called acetate. So that ate ending is basically what you get when you peel the proton off of something. So lactic acid, when it loses its proton, becomes lactate. Citric acid, when it loses its proton, becomes citrate. So acetic acid, when it loses its proton, becomes acetate. Okay, this, of course, is the conjugate acid of water, the hydronium ion. Okay, so the conjugate of a weak acid is a weak base, because this base is actually, so this base here is actually a strong enough base to push the equilibrium in the opposite direction. See that? So that's what makes this so different from a strong acid, strong base situation. You have this is an actual equilibrium reaction. And that means that they're kind of more equal partners. So the conjugate of a weak acid, I'm going to abbreviate that as WA, is a weak base, which I'm going to abbreviate as WB. So I can say that, and I can also say the opposite, that the conjugate of a weak base is always going to be a weak acid. We'll talk about weak bases a little later, because you always have something with enough base or acid strength to drive the equilibrium in the opposite direction. So let's take this reaction for a second and think about what we did in the previous chapter, the equilibrium chapter. And I want us to write down an equilibrium expression for that partial dissociation of the acetic acid. So, of course, what I mean by that, that's a fancy way of saying I want us to write down the K for that reaction. So the K for this reaction is going to be equal to the concentrations of the products. In that case, it's acetate and hydronium over the concentrations of the reactants, which in this case is just going to be the acetic acid, right? I'm going to leave water out of that expression because, of course, water is a pure liquid, so it doesn't appear in the expression for K. What's more, I'm going to give this K a special little subscript, A, and I'm going to write it also up here above the equilibrium arrow, Ka. And all that means is that this is an acid dissociation constant for this particular weak acid. Okay? Well, that's nice. Now, what you can do is measure a specific Ka for a specific weak acid. Each acid has its own unique Ka value. And for acetic acid, the Ka is equal to 1.8 times 10 to the minus 5. And my friends, that value is something that over the course of the next couple of weeks, you're going to end up memorizing. See how small that number is? 1.8 times 10 to the minus 5. That gives you an idea of the fact that at equilibrium, there are way more of the reactant molecule than there are of the product molecules. Okay, that's why this number is so much less than 1. Okay, such a small number. So we can, of course, use that Ka to kind of judge the strength of the acid. And the smaller the Ka, the weaker the acid is going to be. That's just Le Chatelier, right? That's the common sense we've been developing over the last couple of weeks with equilibrium, right? The larger the Ka, the stronger the acid. In fact, when we saw very strong acids last week, like nitric acid or hydrochloric acid, those acids are strong because their K values are just humongous. They're so big that they drive the equilibrium so far forward that there's essentially no backwards reaction. So let me give you an example. We talked a little bit about hydrofluoric acid last week, and you guys were telling me that you thought hydrofluoric acid was a strong acid, and I said, no, it's actually weak. But I said it's one of the stronger weak acids. It has a Ka value of 6.7 times 10 to the minus 4. So you can still see that Ka is significantly less than 1, so that makes hydrofluoric acid one of the weak acids. HCN has a Ka of 7.2 times 10 to the minus 10. So looking at HF versus HCN, which is the stronger acid, HF or HCN? I'll give you a second to think about it. Well, we just have to look for the larger Ka. Of course, this value is much larger than this teeny tiny number over here, right? We're comparing 10 to the minus 4 versus 10 to the minus 10. So comparing those two, we can see that this is going to be the stronger of the two acids, if that makes sense to everybody. So the Ka values give us a useful gauge of how strong an acid is, or how much the equilibrium is going to be driven in the forward direction. So how do we get all these Ka values? Well, Kas have been determined experimentally, and they've been tabulated for your calculating pleasure. So we find Ka experimentally by just measuring the pH of a known concentration of a given weak acid. So I'm going to do some calculations now that show you how we figure out the Ka. So we find Ka experimentally by measuring the pH of a known concentration of weak acid, Wa. Let me give you an example of that. Let's take hydrofluoric acid. I'm going to say that a 0.100 molar solution of hydrofluoric acid has a pH that we measure with a pH meter to be 2.10. What is the Ka of HF, hydrofluoric acid? This is a classic kind of weak acid question. And the way that you should approach these problems is always, 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 always write down the reaction for the dissociation of HF in water. Okay, so here we have HF interacting with water, and that, of course, is an equilibrium reaction, and it has a Ka associated with it. Now, what happens is we're going to have complete dissociation. Water here is going to be acting as the base, and it's going to receive a proton from the HF, and the result is that I'm going to get hydronium plus the fluoride ion. You guys should be able to write an acid dissociation reaction for any acid at this point, strong or weak. The only difference between strong and weak is that when you have a weak acid, you have these equilibrium arrows here. Okay, Well, that's nice. We want to know what's the Ka. So I want to write down an expression for that Ka. I'm going to leave some space underneath it because I want to make an ice chart a little bit later. So I'm going to write the Ka a little bit down here. And I'm just going to base it on the reaction as I've written it. Hydronium times fluoride over the HF concentration. This is what I want to calculate. Now, the only thing I know about this reaction is what it told me, which is that the pH is 2.10. The pH, as I said at the beginning, is simply the negative log of the hydronium concentration. So if I rearrange this equation, I can figure out what the hydronium concentration is by taking 10 to the power of the negative pH. We did that last week. So if I take 10 to the power of negative 2.1, that gives me a hydronium concentration of 8 times 10 to the minus 3. Okay, so I really want to emphasize that. When you're given the pH is telling you what the hydronium ion concentration is at equilibrium. Okay, so that's very important to note that this is the hydronium concentration at equilibrium, not initially, but once the solution has come to equilibrium. So the pH is always telling you that. Okay, so it won't let me write the N because I guess I'm too far over. Let's see, equilibrium. There we go. All right, so, all right. I have an equilibrium concentration. So now what I'm going to do, I'm going to change the color to make this more obvious. I'm going to go back up to my reaction, and I'm going to make an ice chart underneath my equilibrium reaction. This is really calling upon the skills that you developed in the last chapter, chapter 12, or chapter 12, was it? On equilibrium. So we need to figure out the concentrations of HF and F minus. Because what we just figured out from that calculation here is the hydronium concentration at equilibrium. Now, what do we know? Well, going back up to the problem, we were given this value, which is the initial concentration of HF. That molarity is the initial concentration of HF. Now, if you look at the stoichiometry of this reaction, for every mole of this, we get a mole of hydronium and a mole of fluoride. So that means that we have an equimolar amount of fluoride at equilibrium as we have hydronium. So these are going to be the same. Water does not feature in the expression for Ka here, right? Because pure water does not have a concentration. So I can leave that out of my ice chart. It's not important. It's implied that I have no hydronium or fluoride at the beginning. So what's happened here is that I'm basically experiencing an increase from 0 to 8 times 10 to the minus 3. And the reason I'm doing that is to show you guys what the decrease on the opposite side of the reaction is going to be. If I am increasing by this much on the right side to get these equilibrium concentrations on the product side, then there must be a corresponding decrease of that amount, because it's all equimolar, of the reactant on the opposite side. So now I just do the arithmetic. 0.1 minus 8 times 10 to the minus 3. So 0.1 minus 0.008 gives me 9.2 times 10 to the minus 2. So that ice chart enabled me to come up with these values that I can actually plug into the expression for Ka, which is kind of cool. I'm going to take this guy. Let's see if I can do this. Oh, never mind. Okay. Sorry, guys, I'm just a little new to this, so I'm figuring out how to work it. So Ka is going to be equal to 8 times 10 to the minus 3 times 8 times 10 to the minus 3 divided by 9.2 times 10 to the minus 2. How lovely. That means, once I do all of that arithmetic, you can plug it into your calculator, that equals 6.7 times 10 to the minus 4. And that's the answer that I'm looking for, the Ka of HF. So that problem enabled us to, sorry, technical deficiencies. How do I get rid of this keyboard here? Eek. Okay, so sorry about that, you guys. So that enabled us to show that the Ka of HF at 25 degrees is 6.7 times 10 to the minus 4. It's unitless because it's an equilibrium constant. So I hope that makes sense to everybody. Let's think about what that means. So knowing Ka, we can determine a couple of other interesting attributes of the solution. So we can calculate the hydronium ion concentration and the percent ionization. Now, of course, the hydronium concentration would just be running this calculation in reverse, right? Because we had the pH, so that basically gives us hydronium, but we'll do a problem in just a couple of minutes where we basically do this calculation in reverse, and you're given hydronium, and you have to figure out you're given Ka rather, and you have to figure out the pH from there. So percent ionization is important because what the percent ionization is it's the number of molecules in ion form. Literally, the percent ionization is the ion concentration over the total concentration of the acid, whatever we're talking about. So I'll show you what that is by doing another example. Here I'm going to do an example using acetic acid. So if we take acetic acid at 0.1 molar concentration, can we determine the following? First, I want hydronium ion concentration, which is nearly synonymous with pH, so both of those. Can I get the hydroxide concentration? And can I get the percent ionization as defined above? So whenever you're given a problem like this, the problem might not say it, but you always want to assume that you are at lab temperature 25 degrees, okay? The reason we're making that assumption is because at 25 degrees, we have the Kw, which you're going to need to do this problem, and the Kw, of course, is the ion product constant for water, and that's 1 times 10 to the minus 14. So let's tackle this problem. Let's tackle this problem little by little. Okay. The Ka I gave you a little bit before, but if you're not given the Ka, you might have to look it up for a problem like this. So if I look up the Ka for acetic acid, CH3COOH, it's 1.8 times 10 to the minus 5. Once again, the problem might not give you that Ka explicitly. You might have to look it up. So your book has tables of the Ka values in the appendix. There are also some example values within the chapter. And as you're doing practice problems on the OWL system, you can even access Ka tables in owl. So I want to figure out what the Ka for acetic acid is going to be. Now, the acetic acid, of course, I wrote the reaction for it reacting with water just a moment ago, but you should always, again, write down the chemical reaction for what's actually happening in these situations. So I'm going to just rewrite that weak acid dissociation reaction. So that Ka can be determined from this reaction as the concentration of acetate times hydronium over the concentration of acetic acid. Okay, this is identical to what we did just a few moments ago for acetic acid. So now, let's make an ice chart, and we can fill in the things that we know and figure out the things that we don't know using those algebraic strategies that we learned in Chapter 12 for the equilibrium stuff. Okay, so what do we know? Well, not much at the moment. We know that we have an initial concentration of 0.10 molar acetic acid. The rest of it is going to be kind of variable at this point because we don't know how much it's going to dissociate. So I'm just going to put as the change minus x because that's an unknown at the moment. We don't know what that dissociation is going to be. Now, there's an equimolar stoichiometry here. I get 1 mole of acetate for every mole of acetic acid that dissociates. So that means that if I have negative x on the left side, I'm going to have positive x for the stuff on the right side. Once again, we don't care about water because it doesn't feature in the Ka expression because it doesn't have a concentration. So 0 plus x is x, 0 plus x is x. And now I have my so-called equilibrium concentrations, and I can plug them into the expression for Ka. So Ka equals x squared over 0.10 minus x. How did I get that? Well, look back to our expression for Ka. On the top, my equilibrium concentration for this is x. My equilibrium concentration for hydronium is also x, so that's how I got x squared. And then this 0.1 minus x is my equilibrium concentration for acetic acid. So plugging those values into Ka is how I get this expression here, that the Ka is equal to x squared over 0.1 minus x. Now, I'm going to do something shocking but awesome. I do not feel like busting out the quadratic equation for this one. And I don't have to. The reason is, okay, look at this number, 1.8 times 10 to the minus 5. That's a small number, right? That number is much, much less than 1. So you could make a strong argument that the dissociation is actually going to be negligible, so that you could take this minus x part of the denominator and just leave it out, so you can simplify this and say that x squared over 0.1 minus x is approximately equal to x squared over 0.1. That's awesome because now I do not have to go through a quadratic to solve for x. So what I just did there, just to reiterate, is that I assumed that minus x is negligible. Can you read that? It says negligible. Since dissociation is very minor, or very small here. Okay, so now this is kind of cool because I know what Ka is equal to, right? Ka is equal to 1.8 times 10 to the minus 5. So let's rearrange that and solve for x. X squared is going to equal 0.10 times 1.8 times 10 to the minus 5. I can multiply those two together, solve for x. X is going to be equal to 1.34 times 10 to the minus 3. I think I gave you too many digits there. Let's make a fewer significant digits there. So I'm just going to do 1.3 times 10 to the minus 3 to give you 2 sig figs. Now, let's go look at what the problem was asking us for again. All right, we wanted to figure out what hydronium is and what the pH is. And X is the hydronium ion concentration. And then, of course, I can take the negative log of it and get pH. So going back here, this is what our hydronium concentration is. What units? Well, if you guys were here, I know you would all be shouting, molar, because it's a molar concentration. How do I get the pH? Well, that's easy. pH, of course, is equal to the negative log of the hydronium ion concentration. So a negative log of 1.3 times 10 to the minus 3. I kept all digits, so when I did this, this came out to about 2.9. So this is the answer to the first part of the question that I asked. The hydronium and the pH at equilibrium are going to be 1.3 times 10 to the minus 3 molar and 2.9 respectively. Now we need to go, so that was the answer for part A. Now for part B, I had asked you guys to get the hydroxide concentration. So hydroxide concentration is what? Well, there we need the ion product constant. So Kw tells us that the product of hydronium and hydroxide is equal to 1 times 10 to the minus 14. So this is awesome, because if I have one, I always have the other. So I can get hydroxide by taking Kw and dividing it by the hydronium concentration from up above, which is 1.3 times 10 to the minus 3. And that's going to give me a value of about 7.5 times 10 to the minus 12 molar. Awesome. So you can see clearly this value is teeny, teeny, tiny, which should make sense, right? I have an acid here, so I have much more hydronium than I have hydroxide. And I have, obviously, an acidic pH of 2.9, which I should hope for because it is acetic acid. And I hope that it has an acidic pH. So the last part of the question is to calculate the percent ionization, which, as I talked about a moment ago, is the ion concentration at equilibrium over the total concentration, also at equilibrium. However, we made an assumption when we did that problem that minus X was negligible, that dissociation was negligible. So we can do the same assumption to figure out the percent ionization. So for percent ionization, you want to look at the ion concentration. You could take either hydronium or acetate. It doesn't matter. I'm just going to take hydronium over the total concentration of acetic acid at equilibrium. And that's going to be 1.34 times 10 to the minus 3 molar divided by 0.10 minus X. But we said minus X is negligible, so we can say this is going to be approximately equal to 1.3 times 10 to the minus 3 divided by 0.10. Again, because minus X is negligible. That just makes it easier to do the calculation, so I'm going to get about 1.3% ionization. And I want to take a step back for a moment and just emphasize what that means. So you see this number? 1.3% ionization. That is crazy, because that means that if we're looking at this equation for acetic acid dissociating, 99% of the molecules are staying intact. Only 1% of them are breaking apart into the acetate and hydronium. That's what that number means. Okay, so I really want to emphasize that. And this is what makes a weak acid a weak acid. This means that almost 99% of the molecules, so 98.7% of acetic acid, do not dissociate. They remain, quote, intact, unquote. Okay, so I hope that makes sense to everybody. In the next lecture, what I'm going to do is talk a little bit about weak bases. So I hope that you guys enjoyed that. And of course, I would be very eager to have your feedback on it. I'm also going to tell you why I made that assumption that minus X is negligible, and I'm going to explain to you guys when it's safe to make that assumption. But for now, I'm going to sign off. It was a lot of fun talking today. Okay, bye.